Minguzzi from CNRS University of Lausanne, and she will speak about strongly interacting systems in combining potential.
Yes.
Combining potential, exact results.
Thank you very much. So first of all, I'm really honored to be here and very happy to share with you this topic, which is one of my best liked topic. So this is the series of lectures. I will put a small plan here. Is to study the strongly interacting quantum gases in one dimension and specifically under confinement. So first we will study with some introduction. Just that I introduced to you, first of all, some features of one-dimensional systems, as well as the main experiments that are run with ultra-cold atomic gases. Then I will start to describe the model. So the model is a very simple but a very, very rich model. It's the model of Lieb-Liniger for one-dimensional bosons. And then overall, these 6 lectures, we will see the exact solutions for bosons. And we will see in particular the ground state and finite temperature, and also the dynamical properties. And the last part, we will study the exact solutions for more complicated systems like multi-component mixtures and SUN Fermi gases. Okay, and overall, I will present to you some derivation. It will be not the only one. Those of you who like mathematical derivations can try their own, and I will be happy to exchange with you. And so I challenge you to redemonstrate in your way what I'm going to present. Okay. So let me start now from the very basis. So first of all, how do we realize a one-dimensional system in a three-dimensional world? We are going, or is it just a mathematical idea? No, it isn't. We are going, in order to realize a one-dimensional system, for example, you can think of a very tight waveguide, which has transversally a very tight confinement. Let us assume that it is harmonic. This, it turns out to be the most appropriate description for the system we have in mind, that it is ultra-cold gases. So then in this type of confinement, in the longitudinal direction, we can also assume that it is harmonic, but this is completely, well, we will be able to change this assumption. So in general, the confinement along Y and Z is with a given frequency omega perp, and another confinement along X that is given by omega 0. And to be in 1D, first of all, the omega perp is much larger than omega 0. But also, we want the whole dynamics to take place in this transverse level. That means that all energy scales will be smaller than this energy scale fixed by the transverse confinement. For example, the chemical potential for this quantum gas must be smaller than the transverse frequency. Also, of course, the temperature that we are going to study is such that we occupy only longitudinal levels, but we stay in the transverse level in ground state. And finally, for the dynamics, we also want that the dynamics occurs on a typical frequency that is smaller than this transverse frequency. And all this defines a one-dimensional system. And this is actually not just an ideal situation, but it can be realized in several physical experiments. For example, you can think of transport across a channel. You can also think of Josephson junction arrays in superconductors. And of course, the system I already anticipated that we're going to look in detail is the one of ultra-cold atoms in tight atomic waveguides. And also the one-dimensional systems, we will see they are quite special, but they are also the best place where to study strong correlations. In particular, in low dimension, the quantum fluctuations are enhanced. And correlations. So this means that it is the perfect system to understand in a controlled way the effect of interactions. And also, what is interesting to know is that in one dimension, we have really a plethora of methods that we can use, both theoretical and numerical. So from the numerical side, maybe some of you work on that. There is a technique called the density matrix renormalization group, or matrix product state, which works really well in one dimension and allows to treat the ground state, the dynamics. Also, of course, you can use in one dimensions methods like quantum Monte Carlo. Why not? And they are especially useful for finite temperature. And on the analytical side, it is really nice because we can combine exact solution, but also approximate but controlled methods. For example, the Luttinger liquid theory. Or also the generalized hydrodynamics, of which Jerome is a great expert. And concerning the exact solutions, there are two types of exact solution. The first one is called the Bethe ansatz, and it works for homogeneous systems. And the second one, the one which I will present you in detail, is the one due to in the so-called Tonks-Girardot regime, and is valid for confined system, but only at infinite interactions. Okay, so this is it's also interesting that some methods overlap in their validity, so it's useful to employ different methods to completely understand the system of one-dimensional bosons. And so overall, it's really what Sutherland defined beautiful models. You will see they are very beautiful from the mathematical point of view. But it's not only beautiful models, they also have applications. And I would like to list a few of them such that you know that we are not just playing with nice models, that are really useful. The first one is to quantum information. For example, you want to study and compute entanglement properties. We are not going to do this here, but there are entanglement measures that can be calculated. The other application is let's do that, quantum state engineering. That is, you want to create a specific quantum state, and you want to manipulate it. So thanks to our type of solutions, we can make exact predictions even for the long-time dynamics. And another application goes to quantum simulation. Maybe you heard of those. Nowadays, you can use an experiment to solve some problem that you cannot solve by a classical computer. This because through the experiment, you can realize model Hamiltonian, and then you run the experiment to have the answer to the physical question. And of course, you may want to benchmark this quantum simulator. And the way to benchmark it is, for example, thanks to exact solutions. Because in this way, you will test the simulator, and then you will run it under other conditions where you cannot have, for example, the exact solution. And another final application is to quantum sensing. So you know that you can build the sensors with quantum systems. And for example, you want to have a very accurate measurements of gravity or of rotation. And if you consider, for example, particles on a ring subjected to some currents, these currents may be a way to probe the rotation of the system. And so the study of one-dimensional systems on a ring may be used for quantum, to develop new protocols for quantum sensing. In particular, rotation plays the same role of an artificial gauge field. Okay, so more or less, you see that there are many things that we can do with one-dimensional systems. And now let's start to recall a few experimental facts. Yes.
Just about the example from the system you quote, do you consider the edge of the quantum Hall systems as a one-way system in this lecture, or is it something totally different?
So the quantum Hall system in the edge has one-dimensional properties. And these are chiral 1D systems. So I'm not going to cover the chiral 1D systems in this lecture. I'm just covering the usual, with moving in both directions. But it's not very far. Somehow, I think it could be useful for your case, too. Yeah, thanks for the question. Okay, so now I would like to present to you some experimental facts that, or some experimental achievements that have led to realization of one-dimensional quantum gases. So this is also useful because it's you should keep in mind that all the quantities that we are going to calculate can be actually measured in the experiments, and it's also experiments also sometimes ask us very basic questions for them, but are quite difficult and simulating for us. So there is in our field there is a common continuous exchange between theory and experiment. Okay, so in the experimental system we have in mind is the one of ultra-cold atomic gases. So I don't know if you had already presentation on those systems in previous lectures, or probably not. Then I take a few minutes to explain to you what they are. So first of all, it's atomic vapors that are, first of all, you start from a solid, you heat it up, you create a vapor, and then you want to cool this vapor down to extremely low temperature. The temperatures is of the order of hundreds of nanokelvin. And also these atomic vapors are trapped by some type of confinement. In fact, the trap doesn't have physical walls because the atoms would stick to these walls and would not stay so cold. So the trap is an optical or magnetic trap. So I'm not going to go into the details on how this is done in the experiments, but you have to imagine that these are sort of virtual confining potentials. And in this way, and the cooling also occurs onto a sort of tour de force, various steps of cooling that are called evaporative cooling, and then finally one arrives to this very low temperature, and the trap can be, for example, as I showed you, harmonic, but it's also possible to adapt the geometry, and one can also realize various types of traps. But so by these atomic physics techniques, one can reach quantum degeneracy. That means that the density and the temperature are such that the system is in the quantum regime, is in the regime where quantum mechanics is needed to describe the experiment. And in such a regime, for ultra-cold bosons, Bose-Einstein condensation has been demonstrated. So by a Bose-Einstein condensation, I remind you, you all know about it, it's the macroscopic occupancy of a single quantum state. And in the case of a harmonic, so usually it's condensation in momentum space, that is, you occupy the k equals 0 mode. But if you have a harmonic potential, then you are occupying the ground state of this harmonic trap, and it will be a condensation in energy space. That means that this condensate will both be visible as a peak in the density profile, as well as a peak in the momentum distribution. So we see already that for this type of systems, it's both useful to calculate the density profiles and the momentum distribution, because these are experimental observables. And Bose-Einstein condensate display also not only macroscopic occupancy, but also macroscopic phase coherence. This is called off-diagonal long-range order, and I will come back to the precise definition later in these lectures. So the initial experiments, which were run with ultra-cold atomic gases, were creating this type of Bose-Einstein condensates in a weakly interacting regime. But later on, so in the first years, let's say it was done in 1995, it was a weakly interacting regime. That means that you could use elementary methods like the mean field theory to account for experiments. But in a second stage, an important advance was demonstrated by showing that it is possible to tune the interactions. That means that you can both change the sign and the amplitude of the interaction strength among the atoms. First of all, let me tell you what is the physical origin of the interactions. So these are neutral atoms, so there is no, in the simplest case, it's a short-range interactions. It comes from the van der Waals potential. And at ultra-low temperatures, and at ultra-high dilution, as in this case of the experiments, interactions are described by the collisions among these atoms that come cross to each other and then collide and go away. And this type of collisions are described by the diffusion theory, and in particular at low temperatures, it is the S-wave collisions that play the main role. At temperature lower than 1 microkelvin, only collisions can occur mainly in S-wave, because in the other collision waves, there is a barrier. Yes?
Here we consider boundary systems, but we know from the fact that you can't get any concentrated condensate in one dimension.
You are right.
So is this dynamic and this physics really one-dimensional in itself, since we need to, well, three-dimensional at least, to break the Merlin-Wagner theorem?
Perfect. I wanted, this is my next, I will go very soon to low dimension, and I was planning to discuss this point. So indeed, initially, these systems are 3D. These weakly interacting in field, and moreover, 3D. But we are going to decrease the dimensionality very soon. And in that case, you're right, there is no Bose-Einstein condensation anymore. I am going to discuss, you already know it, I am going to present this. First, I finished rapidly the part on the interactions. So interactions are in S-wave. That means that interaction potential can be described as a contact potential, that is by a delta potential. And the interaction constant G is related to the S-wave scattering length, 4 pi h by square over the mass times the scattering length in S-wave, called AS. So in the ultra-cold atoms, it is possible to tune the scattering length by a mechanism called the Feshbach resonance. That modifies the interparticle potential by applying a magnetic field. And so in this case, the scattering length as a function of the magnetic field may display a resonant behavior. And physically, what happens is that in the two-body potential, you create a new bound state. And when you study the scattering near, when you calculate the scattering properties of a potential that has an additional bound state entering, for example, by tuning the bottom of this effective potential, of a particle-particle potential, then you get a resonance in the scattering length. That means that here the interactions are very large and positive, repulsive. And here the interactions are very large but attractive. So both regimes are extremely interesting. In our course, we are going to focus on the repulsive case. But there is also very beautiful theories for the regime of attractive interactions and also exact solutions for this case. But okay, I had to make a choice. So what you have to remember from this part is that this system is absolutely tunable. And so we are allowed to tune the interaction strength and this is another way to imagine, to treat a quantum system. Usually the quantum systems in experiments have a fixed value of interaction strength, and you change something else. You can tune the densities or the other properties. Here, we can also tune the interaction, and we are interested to go to very large interactions. Yes?
Can we see with experiments that as we change B, is A zero as like a discontinuous jump from being positive to negative, or in some cases
Well, yes, whether in the yeah. Yes, so in fact, you cannot physically arrive to infinity, but what I have demonstrated in the experiments is that they arrive in a regime where the interactions are so large that it's really very close to the infinite interaction regime. In 3 dimensions, with attractive fermions, for example, this is called the unitary regime. For 3D fermions. And in 1 dimension is the regime we are going to study. It's called the Tonks-Girardot regime. Yes, but your question is very physical and very important. Thanks. And let's see. Yes, so now let me also mention that we are speaking about equilibrium and reaching a given quantum state because these systems are extremely well isolated. That means there is no coupling to an environment, so there is not much decoherence. And then, well, they are still metastable, so it means that at some point they will decay. But it's quite a slow process, and they have a lifetime of a few seconds, which is actually quite a long lifetime, taking into account the intrinsic time scales or the order of millisecond for the dynamics. That means that we can really consider them to good precision as thermal. Of course, the dynamics of decay is also very interesting in itself, and it's another topic that Jerome has studied in detail. And for example, he has studied the effect of the theoretical description of atomic losses. But I will not cover this part in my course, so I will assume that they are really well isolated. Yes?
When you say that these systems are very cold, given it's around 100 nanokelvin, well, usually the temperature we need to compare this temperature to is the Fahrenheit temperature in the systems. And so are these systems really at a very low temperature compared to this Fahrenheit temperature? Or are these systems, well, what is the comparison?
Yes.
Order of magnitude in between the two?
Yes, okay. So thanks for the extremely good question. Indeed, we are extremely cold in the sense, so in general, we can compare with the de Broglie wavelength. And for example, the quantum regime is such that the density times the density in 3D times the de Broglie wavelength cube is larger than 1. And the de Broglie wavelength is 2 pi h bar square over m kBt. So indeed, the temperature, to reach the quantum degeneracy, we need to be at sufficiently low temperatures. For fermionic gases, which was my next, I wanted also to mention those. Indeed, this corresponds to a temperature that is smaller than the Fermi temperature, which is defined as the Fermi energy divided by Kb, Boltzmann constant. Now, how cool can we go with fermions? Well, we can go to, 0.05 TF, I guess is the best they can do. So, or 0.1 TF. So if you compare to electronic systems, it's cold, but not ultra cold. somehow in view, as with respect to their own Fermi temperature, they are still quite hot, although they are really cold in absolute temperatures. Yeah, so as the question, we had the question on fermions, let me also say a few words of those, about those. So indeed, and it was not only possible to cool and trap bosons, but it's also possible to cool and trap fermions. So for that, it is enough to take an atomic isotope that is fermionic. And it has been also demonstrated the reach of quantum degeneracy around 99. And for those systems, it's actually more tricky to cool them, because usually for the bosons, we exploit the collisions among particles, but since the collisions are in S-wave, there is no S-wave collision for spin-polarized fermions because of the Fermi statistics. So you need to use two components that I indicate like spin up, spin down, although it's a sort of pseudo-spin. And in this case, we can have S-wave collisions. And thanks to this type of collision, that it was called sympathetic cooling, because to cool, you needed the two species. It was possible to obtain the quantum degeneracy regime for fermions. And later on, it was also demonstrated that it's possible to realize interacting Fermi gases and repulsive interactions, and this regime, well, I'm going just to tell you in a second. Okay, so then a few words about the geometry and how to reach to the 1D regime. That was the question. And how do I go from a 3D, like that, spherical trap to a one-dimensional world? And there are two methods. The first method, so this is about going to 1D. The first method is to use optical lattices. In fact, as we have atomic vapors, they are subjected to light forces, and if you use a standing wave of light, the atoms and the atoms are far detuned for an atomic. This light has a far detuned from an atomic resonance. The atoms feel a potential, a trapping potential that is proportional to the intensity of the laser. And so the atoms feel the maxima and the minima of a lattice, perfect lattice potential, perfectly sinusoidal. And if you apply this in several directions, you can create low-dimensional structures. For example, to go to 1D, you can apply laser light in two directions in such a way that you create tubes, okay? And this is the way, in the experiment, they managed to go to 1D. And there is, the tunnel among the tubes is negligible, but it can be actually tuned. So you can also imagine a dimensional crossover from low dimension to higher dimension by tuning the tunnel constant among the tubes. The other way to go to 1D is to use the so-called chip trap. So you know that when current flows into a wire, generates some magnetic field around it, and the magnetic field generated by this current flowing can be used to create a one-dimensional tube, one-dimensional trap. And in this case, in the optical lattice, as you can visualize, you have several tubes like that, also making onto a lattice in 2D. So the top view so the side view would be that, several tubes perpendicular to the blackboard. while for the chip trap, we have just one tube. So for some experiments, it's quite practical to have just one tube because you have one realization of a single quantum system, while in this case, the signal will be the average over all these individual tubes. It's a bit more complicated. Good. So last point I would like to mention before going on to the theory part is, let me clean this one, is to make a very short history of some experiments that were really important for the 1D community. And this is an extra motivation for you to learn about the one-dimensional systems. So the first one, and by the way, I just made a small choice, but there are several experiments on 1D atomic acids. I just made my personal choice. So the first one is the demonstration of reaching the strong interacting regime. Let's say interactions very large and positive. This one was achieved in 2004 by two groups, Emmanuel Bloch, team, David Weiss. And so this is a really important step because it demonstrated that you can achieve experimentally strong interaction. Why was it not sure? Because at strong interactions, you may have particle losses. And then, okay, you tune your knob, but at the resonance, you may start losing all the particles and you cannot actually study it. And this is what happens in 3D. In one dimension, we are lucky that collisions are suppressed by the fermionization mechanism that I will present you. And so it was possible to reach the strong interacting regime. How did they see it? They looked at the shape of the momentum distribution. And that's where it was, so they showed that it was different from the one of a weakly interacting gas. And it agreed well with the theory of infinite interactions. So this answers the question that I had before, how close are we to the strongly interacting regime? We can check by comparing the observables to the measured ones. So that was shape of the momentum distribution. And the other experiment was looking at the width of the density profile. Because you will know why in the end of the second lecture. So let's say this regime can be reached. Then the regime can be studied. And the second experiment that was really occupying the theorists for a long time is called the quantum Newton's cradle experiment. So the Newton's cradle is something you may have had as a toy when you were a kid. So there are some balls, and if you launch one ball against the others, it starts oscillating back and forth like that. So this is the Newton's cradle. And experimentally with ultra-cold atoms, they started from a trap like that with a 1D gas in the center that was split in two parts, like that, so not anymore here. So they were giving a kick in two directions, like that. And then it started to oscillate, and the two wave packets were going across each other, back and forth. And quite surprisingly, in one dimension, these oscillations were really, really occurring for extremely long time, and only in one dimension, while by decreasing a little bit the barrier among the tubes and allowing to go to coupled tubes, in 1D long time oscillations, if the tubes become coupled, and so let's say we go to sort of 3D-like, then oscillation would decay very rapidly and dump. So this showed that the 1D regime is very peculiar, and moreover, these oscillations were large amplitude oscillations, so it was very challenging from the theory point of view. And again, this was another topic that was studied by Jérôme, and there was a very successful theory, the generalized hydrodynamics, that finally accounted for this experiment. But conceptually, it was really very important because it showed a very strongly out of equilibrium situation, which is the most difficult to describe from the theory point of view. Another experiment that is really really interesting for us is occurred. So this was around 2006. Another experiment on bosons that is interesting for us was measured much later in 2021, I would say, and this was demonstration of the dynamical fermionization of bosons. So the setup is quite simple. In this case, you always start with this harmonic trap with one-dimensional bosons inside, and you allow for a one-dimensional expansion inside the tube. So initially, the gas is, you have a very, very long trap, like that. Initially, the particles are confined, and then you turn off the confinement, and you let the cloud expand like that, but only in 1D. And in this case, it was demonstrated that the momentum distribution at long times tends to the one of a Fermi gas. Yes, okay, so welcome back. We had a forced break. I wanted to finish the list of experimental realizations that are very useful before we attack for the theory part. I want just to mention two experiments on one-dimensional fermions. The first one, so it was our number 4. The first one is called fermionization of fermions. And let me explain, is what is done by the Selim-Joachim group in Heidelberg. And let me explain what it is. First of all, they had very few fermions. Take, for example, 2 fermions. One spin up, one spin down. If you have fermions in a harmonic trap, all spin up, you know that you can put them one by energy level. However, if you have spin down, you can adapt 2, one per type of color in each energy level. However, now if you turn on interactions, G up down, to very large values, then you cannot anymore put up and down fermions in the same level. This is the fermionization of fermions. So then up to permutation of the particles, you are obliged to do something like that. This is the fermionization of fermions, and that was experimentally measured. And the last but not least example that I want to mention on experiments is the study and realization of one-dimensional SUN Fermi gases. And this was done here in Florence in the group of Massimo Minguzzi and Leonardo Fallani. And they were using ytterbium atoms that has many internal components, so up to n equal 6 components. So in this case, it's not anymore a spin, but you have to imagine it as a color. I do not have 6 colors, sorry, but blue, white, oh, maybe 5, and so on. And then, well, okay, and this is black. And it was possible to manipulate and trap this multi-component Fermi gas with large repulsions. And in this case, it was they were characterizing it again by looking at the momentum distribution at a collective excitation spectrum. So this is also a very nice model for the theory, and it's very challenging also for this case. In special conditions, there are exact solutions. Okay, so that I said Leonardo Fallani group. Okay, so this concludes my overview of the experiments. Now let's switch back from now on forever to the theory. And before, yes? It means that we have Fermi gases which have an internal, so like for fermions, you can have spin. For let's say electrons, you can have spin up and spin down. For atomic systems, you can have several internal atomic levels that come from the atomic physics, and so you have 6 equivalent ytterbium atoms. They have like a label that allows to distinguish them. And this is done by playing the tricks of atomic physics. And that means that you have to imagine that these fermionic particles have like the equivalent of color, I may say. So that means that when you are going to describe them, they can have collisions between the blue and the yellow, the blue and the red, and so on. And it's just a 6-component mixture of fermions. They have, okay, so is it?
Yeah. If I may comment, because we had a seminar by just last week.
Ah, okay, perfect. Okay, great.
Students are usually surprised because, of course, you could interpret this as a spin, what is 3 over 2 C, 5 over 2. Spin 5 over 2 represents.
Ah, no.
So this can get confusing. But actually, this is because they are generators. I mean, this actually appears to be, maybe we can go further.
Okay, we will see the symmetry structure in the last lecture. It's not a spin system. It is described by a more complicated Young tableau, if you wish, if you want to. So, and the way is, yes, so for the moment, keep it as a sort of internal label. The Hamiltonian for this system, it has, okay, a kinetic part that is this, and then there are interactions among the particles belonging to 2 different colors. And the interactions are the same for all this type of, so yellow with red or black with white, they all have the same interaction strength, and that's what makes the SU6. Yes?
You reach the SUN level to limit all the, well, 6 configurations to get the same energy, or can you have similarly to the Siemens like splitting in your structure?
Okay, they must have the same energy levels.
Yes, so the answer from the seminar was that we have the SE2 rotation or spin-slot symmetry, and both of them commute with the Hamiltonian, therefore we have an extended symmetry which corresponds to SU1.
This is perfect, yes.
So we have additional symmetry to SU.
Yes, perfect. Thanks. Okay, good. So I now switch to the theory. I want to address very briefly the question that was raised about what is the fate of a Bose-Einstein condensate in one dimension. As this is the very last part of the introduction. As one of your colleagues already noticed that no, we cannot have Bose-Einstein condensation in one dimension. I will leave it as an exercise. So for free fermions, sorry, bosons. I'm sorry, I was still in the SUN world. For free bosons, it's elementary to show that if you want to calculate the thermodynamic properties and if you want to determine the chemical potential as a function of the number of particles or the density and the temperature, you do not need to invoke Bose-Einstein condensation. So, in fact, you can try already for free bosons that no, there is no BEC in 1D. And more generally, this is due to the Mermin-Wagner theorem. That says that there is, the quantum fluctuations are too strong. And actually, for any non-zero temperature, for this case of ultra cold, for this case of bosons, you have that assume that there is a non-zero condensate fraction, then you would have this inequality. The momentum distribution or the occupation number of particles of momentum k non-zero should be larger or equal to n0 times the temperature, kBT, divided by kh bar square, k square over 2m, the free particle energy. So you see that imposing that the total number of particles is finite, that is the sum over all k of nk, let me put it as a sum over k non-zero of n of k should be the total density minus the condensate density. You see that in one dimension you get a problem due to this k square denominator, and hence the only solution is that n0 must be 0. And this is expressed at all non-zero temperature. If here you put T equals 0, well, you cannot say anything about the n0. In this case, you have to use another theorem that is demonstrated by Pitayevsky and Stringari. And this one says that at T equals 0, another inequality, n of k must be larger or equal than the presumed condensate fraction n0 divided by 4 times the static structure factor s of k minus 1/2, which plays essentially no role. So S of k is a quantity well known in the theory of quantum fluids and quantum liquids. It's called the static structure factor. And it is the Fourier transform of the density-density correlation function. And so now to know whether or not we have Bose-Einstein condensation, we have to look at the behavior of S of k for k going to 0. And it's known, or it can be demonstrated, that for compressible fluids, you have this S of k is proportional to k, so some constant times k. And then, in this case, you see that still, by the same argument that we used at finite temperature, we arrive that N0, the condensate fraction, must be 0 as well. So there is no Bose-Einstein condensation even at 0 temperature in one dimension. So what is left? Well, what is actually happening in one dimension is that the phase fluctuations, the phase of the fluid, phase fluctuations are extremely important. And to know that, we introduce a quantity that is called the one-body density matrix, and we study it. So this one-body density matrix, or for the people who do optics, is the first-order correlation function. So they call G1, but I call it usually rho 1 of x and y, is defined as the expectation value of psi dagger x, psi of y, where this psi with a hat on top are the bosonic field operators. Usually, I will work in second quantization, but sometimes it is faster to define things. Sorry, in first quantization. Now, oh, sorry. My micro. Sometimes it is faster to write quantities in second quantization, so I hope you will be able to follow from first to second quantization. It's quite straightforward. So this is defined in second quantization. This satisfies the usual bosonic commutation relations. Delta of x minus y. Okay, so this quantity is the quantity that tells you about the spatial coherence of a quantum fluid. You destroy one particle at position y, you create a particle in position x, generally different from y, and if you look at large distances between y and x, you are going to check whether the system is still coherent on such long scale. So this is what we want to probe, is what I mentioned at the first hour of diagonal long-range order, is when at large distances you have that x minus y is going to infinity. It goes to a constant value. This constant is exactly the condensate fraction. This was called Penrose and Onsager criterion. And it is the most general definition that I know of Bose-Einstein condensation. Andrea has also worked a lot on this topic and has made very important contributions. So now what happens in one dimension is the following. So the rho 1 of xy, calculate exactly this phase-phase correlator using a theory that is the Lattinger liquid theory. So I think there is no time to go through the derivation here, but if you have questions, I can show you the derivation at the question time, or you can do the exercise on your own if you know the Lattinger liquid theory, or probably you have already calculated it in this case. Anyway, at large distances, it decays as a power law, where this capital kappa is a parameter that enters the Lattinger liquid theory.
Sorry, do you think it's possible for you to write slightly bigger letters?
Yes.
Just slightly bigger?
Okay, sure, thanks. Yes, yes. Okay, so you see that the one-body density matrix in one dimension decays as a power law with the distance. This shows that there is no Bose-Einstein condensation, and moreover, this decay is due to the phase fluctuations. It's really the phase fluctuation part that accounts for this decay. So what is this? So truly speaking, there is no off-diagonal long-range order. However, this all depends on what is the value of this parameter kappa. And the kappa is a function of the interaction strength for bosons. Takes this form. This is the value 1 at large interactions, and it diverges at small interactions. So if kappa diverges, it means that this decay is really slow. And then, so to summarize, we have one regime that is at weak interactions. We have, say, small phase fluctuations. And then we speak of a quasi-condensate. That means a condensate with a fluctuating phase. However, at strong interactions, the phase fluctuations are larger. And in this case, there is no Bose-Einstein condensation at all. So the picture of a quasi-condensate with an almost well-defined phase does not hold. And so for going from weak to strong interaction, the physical regime is very different. Okay, so yes?
But if we, so the argument that you said there, is it true also of finite size or finite size systems? Because then in experiments, they don't work with size. We get something which is finite, so I don't know whether this can use something, can represent something which seems like a EEC, but then it's not, so then I don't know how one can really see the difference between weak and strong interactions, see whether they are going to have EEC or quasi, let's say.
Excellent question. So that's true that if you are in a finite size system, you can you have a sort of cutoff of the phase of the fluctuations due to the fact that the system is finite. Now still, but this must be checked explicitly when you do the calculation on the finite size system. You can recognize very well weak to strong interaction. And one reason being, but you cannot know before doing the calculation, so for example, at very strong interaction, we know, so you will see soon, that you cannot put more than one particle in a given energy level. And in that case, for sure, it is very far from a Bose-Einstein condensate. Concerning the observables, I will also show you that there are, anyone that you want to calculate, you will be able to tell that you are in weak or strong interaction, and the signal will be very different. But it's really important, and when people were starting to study the coherence properties of this low-dimensional system, there were works by Shliapnikov and Petrov that were exactly trying to study a sort of crossover by changing the temperature and changing the interaction and the size of the system, and they have made a specific phase diagram for that.
Are these property only true for short distance interaction, or are they also true for infinite range interaction? For example, Colombian interaction, something like this, which might be quite troublesome, like depending on the dimension.
Most of the results that I will derive is only for short-range interactions. For long-range interaction, the physics is different. There is one model that is solvable, the Calogero-Sutherland model that has long-range interactions, but yeah, I'm not covering that one. Yes, actually, really the core of the solution is because the interactions are short-ranged. Good. So in the last part of this lecture, sorry, yes.
Are you seeing here that the fragments are spinors? There is no up-down.
I'm back to bosons, so yeah, there is no, but there will be, you can also think of bosons with an internal levels, so you can also think of spinor bosons, but not now, not yet. Let's say, so far, just a single component bosons, and then we will include the multi-component case towards the end of the lectures. Okay, so now time for going to the model. So, and I really thank you for all the questions, because exactly now I'm going to write the Hamiltonian. And so I will specify which type of interaction potential. Okay, so model. So from now on, I will work in first quantization, because it's very simple to write things. So I think it's but please, you can rederive everything. For sure, you can rederive everything in second quantization. So if you want, go ahead. So in first quantization, the model Hamiltonian that I am using is a non-relativistic model of n bosons of mass m with interaction strength G. And I add also an external potential, one-body potential Vx. And we have in mind our harmonic trap potential that is found in several experiments. So there is the kinetic part, there is the external potential, and then I have the interaction, sum of J is smaller than L. I'm sorry, tell me if the letters are too small. G delta of xj minus xl, and the sum run otherwise always 1 to n. So this model is a very well-known model. It's called if I take to zero the external potential, this is called the Lieben-Liniger model, which was introduced and studied in the 60s, last century, and which is amenable to an exact solution in for Vx equal to 0. Exact solution by the Bethe ansatz. The interaction strength that I put here is a one-dimensional interaction strength. I will call it G in general to make short, but it's not the same as the three-dimensional one I just presented in the first lecture. It is related to this three-dimensional one, but it in reduced dimension. So in this case, I take into account the effect of our tight atomic waveguide to describe atomic collisions in a waveguide. And this gives rise to a sort of effect of resummation of the transverse levels to renormalize the interaction from 3D to 1D. And it has this form, 1 minus the scattering length in 3D divided by the transverse harmonic oscillator length times some constant, alpha. And then there is a dimensional term that is, again, the harmonic oscillator length And the harmonic oscillator length is the square root of h bar divided by the mass and the frequency of the transverse confinement. And this constant is a numerical constant. So this is a precise expression of what we have to input in the one-dimensional Hamiltonian, knowing the result of the collision properties in 3 dimensions. And this equation was found by Maxime Olshany in 1998. So, in the presence of the harmonic confinement, so there is, it is not anymore integrable by Bethe ansatz, but we are going to have an exact solution with the Tonks-Girardot method. Okay, so how many of you are familiar with Bethe ansatz? Okay, a subset of you. So I will very briefly sketch the idea of the Bethe ansatz solution without going too much into detail, but again, do not hesitate to ask at the question session. So the reason being that it has this Bethe ansatz solution has several elements, and it allows me to introduce some vocabulary and some concepts that I will also use for the exact solution in the presence of an external confinement. And so I think it's a useful intermediate step. But I will not give the full derivation. So let me devote one slide to the exact Bethe ansatz solution. One slide, one blackboard. This solution was provided by Lieb and Liediger in the 1965. And the idea is simple. Since we have a contact interaction potential, you see that when xj is different than xl, then you have a free problem, a non-interacting problem. But when xj is equal to xl, I have a delta condition. So that means that in general, we can replace interactions by a cusp condition on the wave function. And in general, we, thanks to this ansatz, for those who don't know it, we want to write explicitly the many-body wave function. So the goal is to have some expression for the many-body wave function, psi of x1 and xn, that is the solution of the many-body Schrödinger equation for this problem. So the first step is to derive this cusp condition, that is to know how we can fix the behavior of the wave function when 2 particles meet. So to derive the cusp condition, and this is very important because we will use it also for the solution in the presence of the trap. The cusp condition, let us take, for example, just 2 particles. And this is actually, we will find out that it is completely general. If I have the Schrödinger equation for 2 particles, I write everything, masses, etc., but of course you could rescale, plus g delta of x1 minus x2, and then psi of x1, x2 equal to some energy level E times psi of x1, x2. Okay, I didn't put the external potential so far, and I leave you as an exercise to demonstrate that the cusp condition is the same also in the presence of an external potential that is, well, for example, our harmonic potential. You can also derive which condition should be put on the external potential. So anyhow, take this to start with. Now you see that to solve this equation in general, it's useful to introduce, to go to the relative and center of mass coordinates, because this interaction potential depends only on the relative coordinate, x equal x1 minus x2. Capital X is the center of mass of this pair of particles. And then you see that the center of mass part is a free problem, and it can be factored out. And so we can write the two-body wave function in this case as a relative wave function which depends only on the relative coordinates, and the center of mass wave function that depends only on the center of mass coordinate. And we want to solve only the relative problem. This is already solved. Oops. Okay, so if we write on the relative coordinate part, and we have a single particle Schrödinger equation in terms of which has a delta barrier, a position at x equal to 0. And then this has as eigenvalue, an eigenvalue epsilon, that is the initial one minus the center of mass part. Okay? This is quite standard, but I prefer to do it in detail because it's a really central step in the integration. So now how do we proceed? You probably did it already as an exercise. You know, we integrate over a small distance around the x equals 0, the whole equation. This part gives 0, and here we get minus h bar square over m dx of psi rel at 0 plus minus dx of psi rel at 0 minus plus g psi rel in 0 equal to 0. So this is the cusp condition. It's called the cusp condition. It gives a relation between the derivative, left and right derivative of the wave function near the position where two particles meet. And we can, of course, rewrite it by putting the constants all at the same side. Okay, so now we are going to use the cusp condition for the Bethe-Ansatz solution. Okay, so the solution, the ansatz for the many-body wave function is the following. You take it as a sum of plane waves. You sum over all the possible particle permutations. You have amplitudes that have to be fixed, and then you have an exponential of the sum of plane waves, k of p of j times xj. And Now it's useful to introduce the concept of coordinate. So this permutation belong to the Sn. The permutation are n factorial terms and are the permutation of n elements. And it is now useful to introduce the concept of coordinate sector. That is, we order the whole huge set of possible positions of the particles can be ordered, and this is only valid in one dimension. So for example, I can take one sector where the first particle is before the second, before the third, and so on. So this is the identity sector. And then another sector could be whatever, x of p of 1, smaller of x of p of 2, smaller of x of p of n, where p is one of the permutation bringing the integers 1 to n onto another set of where you permute them, p of 1, p of n. Is it so far the notation sufficiently clear? Probably. Yes?
So does each permutation define a different coordinate sector?
Yes. Okay, so and then you see that since this is a bosonic wave function, once I find the solution in a given coordinate sector, I find it everywhere because of the bosonic symmetry under exchange of particles. So the goal is just to find this wave function in a given coordinate sector. And and there is another thing that I have to say. So as I already anticipated, but let me repeat it and once more. This is valid only in the homogeneous case. And there are two possible cases that you can imagine. One is a box with hard walls, and the second one is a ring with periodic boundary conditions. And as it's written here, it is this second case. We are describing bosons on a ring. This other case is also integrable by Bethe ansatz, but it takes a bit more effort and chalk. So usually people work on this one. But just for you to know, there is also the other case that is integrable. So now we want to determine these amplitudes AP. How am I doing with time? Yes, 10 minutes. So, and then for that, we impose the cusp condition for each pair of particles when they meet. So, let's see. Well, okay, I will sketch the demonstration. So, okay, no, but okay. So let's take one permutation P such that we have, that brings, okay, and now permutation can be equivalently applied to the to the index J of Xj or to the index of the wave vectors K that we use to build these plane waves. So don't be surprised, sometimes it's K of P of J, sometimes it's Kj X of P of J. So the permutation can, of course, only permute the K. So we go from K1, Kn to a 1, which has P and Q in the positions 1 and 2. And the other one is K alpha 3 to K alpha n. And consider now the other possible permutation, which brings the same onto the case where you exchange Q and P. And the rest is the same. So this is, shows that it affects the coordinates x1 and x2. Now, that means that the corresponding terms in the many-body wave function are the following. AP, and then with P, I have P and Q in front of x1 and x2, and so e to the IP x1 q x2 plus all the rest. And the other one, the one associated to Q, is AQ. And in this case, Q is for x1 and the P for x2. And the rest is the same. So why can I focus only on a single pair of permutation? Because I want to derive a solution that is valid pair by comparing all the possible contributions, okay? So I can stick to these two for the derivation, and then the overall sum will be satisfied automatically because I satisfy term by term. Okay, so now I plug in, I calculate the derivative of the wave function. Small p and q are two, I make a choice of two permutations. The first one, which has wave vectors in correspondence to the position 1 and 2, the wave vectors that I call p and q, small p and small q. And the other permutation is the one where I exchange these two. And that means that in the wave function, there will be one term where I have px1 plus qx2, and in the other is qx1 plus px2. And now when I I can calculate explicitly the derivative. For example, d over dx2 of psi for x1 equal to x2. What does this give? It gives IQ AP. So the overall wave function then is this plus all other terms. Okay, so there is IQ AP plus IP AQ times psi tilde, which corresponds to the rest of the wave function. Okay, and you can rederive on your own. Similarly, the second, the derivative with respect to x1, this was my cusp condition. I will put it somewhere on this blackboard. The cusp condition, I will put it in this blackboard here. The x psi of 0 plus minus the x psi of 0 minus equals the mg over h bar square psi of 0. Okay.
Why are we just permitting two? Should we be permitting all of them?
Yes, I tried to say this. We just do two because we are going to impose that if for each of the two permutations there is a relation that holds, then it will hold for the whole sum. Okay, so we can just do one pair by pair. So then it will be automatically satisfied for the whole sum if it holds for all the pairs independently.
This is like when you compute that derivative, basically on the right side
for x, yes, but none that involves the p and the q permutation. These are the only two which concern the two permutations we are looking at. Similarly, the x1 of psi is Italians move a lot. When they see. The second one is P, AP plus IQ, AQ times the psi tilde. And now if I apply the cusp condition, by combining the two, I have Q minus P times AP, but I see that there is the same with a minus sign with AQ. So I get AP minus AQ. And then I have the position, so the term associated with the wave function in 0. And let me just also call all these C to make it, to stick to the usual Bethe-Ansatz notation, and furthermore, it's faster. So this will be equal to C times AP plus AQ. And on both sides, I factor away the psi tilde. So if I combine these together, I can get AQ as a function of AP. And you have to check if it is true, that it should be AQ equal minus AP. And then we have this term, C minus I Q minus P divided C plus I times Q minus P. In other words, this can be written as minus EP exponential, times a phase theta of PQ that is defined by equating these two. So in fact, theta of QP, you can also check and as exercise is minus 2 arcotangent of Q minus P over C. Okay, so this is the important phase, theta, that enters in the Bethe-Ansatz solution. And now I will just conclude by writing the final Bethe equations. And let's see where I can write them. Maybe on this blackboard here. Sorry. There. Yes? And here I didn't put the plus or minus. Yes, you are right. No, it's just a plus or minus. In fact, it is up to a sign for the ground state, it will be the same. So indeed, sorry. Let's put this, for example. And very well seen. The other derivative will be same in magnitude, but different sign. In essence, the cusp is something like that. And yes, we will see tomorrow. Okay, so to conclude, we have so far determined a relation of what happens when we change coordinate sector, but we still have to fix the values of the k vectors. What do we do when we have non-interacting particles in a given confinement? We know that they are discrete and they are fixed by the boundary conditions, right? So it's exactly the same for the Bethe-Ansatz. And to find the values for the kj, we have to impose the boundary condition. Remember, we are on a ring. So now when we are on a ring, it means that one part, we have to impose as conditions that the wave function, for example, for xj equal 0 at fixed all the other coordinates, is equal to the wave function for xj equal L at all fixed the other coordinates. And that means that one particle has to cross all the others and come back. So we impose the periodic boundary conditions, and this means that after having made this turn, we have 1, let's say the wave function here, is equal to e to the I kjl. This was the part of the x. But we also see that by crossing n minus 1 particles, we have a minus sign here and a phase there. So that we have a minus 1 to the n, and then we have e to the I, and then this sum over all the phases, theta of kl minus kj. L1 to n, but okay, it vanishes for L equal j. So this is the constitutive equation which determines the wave vectors, which is usually written in logarithmic form. And this is the final expression that we will arrive today. And in logarithmic form, it is a set of equations for the kj. So it is, first of all, this term here, or the fact that when you take the logarithmic form, you get some integer or half integer, ij, integer or half integer, depending whether n is odd or even. And then we have the phase that we have shown there, the arcotangent. So sum over L, arcotangent of KL minus KJ over C. So for each J, 1 to n, we have a set of coupled transcendental equations that fix the values of the wave vectors K. And you see that in general, for finite interaction strength, they are coupled, and they form an effective Fermi sphere. So you see that interacting bosons they are described by this set of kj's that form a sort of Fermi sphere. This kj needs to be determined by this solution. If you have a too large number of particles, there is also a, let's say, you can transform this sum onto an integral, but this is done in the Lieb and Lineger paper. I'm not going to do that. And for the limit of 0 interactions is not included, is actually singular. It's trivial and singular at the same time. It's trivial because if you have no interactions, it's just free bosons. You do not need advanced solutions. But it's also singular because it's the case where all this Fermi sphere collapses in one point. So it's a sort of excluded by this treatment. For any finite interaction, instead, we have this sort of Fermi sphere. And for infinite interaction, then this term vanishes. And so for C tending to infinity, then it's the case where the kj are only fixed by integer or semi-integer values. Okay? And this is a first hint, let's say, or of the fact that so these are integer multiples of 2 pi over L, is similar to the free particle solution. This was exactly the point where I should stop, and tomorrow we will restart from this point and derive the solution for the harmonic, for the general confinement. And if you have other questions, I am still available. Oh, yes. First this and then.
Review the steps of the calculation for these two particles again.
To this one here,
Yes.
this and here, or maybe before. I don't know. So the cusp condition, the cusp. You mean the cusp condition for two?
Cusp condition, but the calculation involving combination speed.
Ah, okay. Yes, yes. Yes. So, by the way, this follows the original work by Lieb and Lineger. So you can also find all the definitions and all the intermediate steps of the derivation in the paper. But let's see. So first of all, I write the full wave function. Let's start from here. In general, I write the wave function as plane waves where I consider all the permutations. The way it's written, the coordinates are xj, but in each different coordinate, for each term of this permutation, the k are attached to the x in a different way. So you imagine I have k1, k2, k3, and then in one sector, the wave function will be k1, x1, k2, x2, k3, x3. And in another sector, it will be k2, x1, k1, x2, plus k3, x3, right? Something like that. And how do I go from this to this? I exchange 1 with 2. So for me, this would be the p equal 1, 2. Okay, so in general, I have a huge number of all these permutations, and I want to know how these amplitudes change, or how to fix what happens when I go from this sector to this sector, how I should match the wave function. And to do that, then I impose the cusp condition, because I know that so this 0 means, for example, x1 equal to x2. 0, it was the relative coordinate. So I want to know what happens when, because you see, if I have 2 coordinates, I can look as a function of x1, I fix x2 somewhere. So this part here is x1 smaller than x2. And this part here is x1 larger than x2. And this is when they are the same. So I have one wave function here and one wave function there. And I want to match them in such a way that it satisfies the cusp condition. And then to do that, I just, well, maybe you should do as an exercise just for 2 particles. And then you see that you have to fix the prefactor of the wave function here and the one there in such a way that it has this shape. Okay.
I mean, like, I had a similar question, but this I actually understood. What I didn't understand is, so once you write down those derivatives for this, like, p and q, and then what I don't understand is how you get this condition for AP and AQ, because I understand you're using the cusp condition, you have the derivatives only from the left-hand side, so...
Yes, yes, but in this case, there is something that I said but I did not write, is that the derivative on this side and on this side, up to a sign, they are the same in the ground state. This is an extra hypothesis, and in this case, then the other way of writing the cusp condition is to say that if dx of psi of 0 minus is minus dx of psi of 0 plus, I can also get the cusp condition like 2, a factor of 2, dx of psi of 0 plus equal to c psi of 0. It's in this way that I am using now the cusp condition there.
So these wave functions are going from the ground state?
So far, okay. No, it's actually, we have to choose, we can calculate also the excited states by changing the ij, but indeed, that means assuming that is always true, that it is left and right the same also for the excited states. So far, to the best of my knowledge, is always the case. To get the ground state or the excited state, I have to choose the ij there. Yes, I didn't specify that. These integers for the ground state are a sequence of consecutive integers, while for an excited state, they can have holes. For example, for n odd, we have this from n minus n minus 1 over 2, 0, and then n minus 1 over 2. And it forms a sort of a Fermi sphere then.
So this is why you said that we are in fact Fermi sphere.
Yes.
I mean, it's a posteriori. Now we can find it.
We, in general, yes, in general, we know that we need n wave vectors to describe the system. And indeed, in the ground state, they form as a sort of a Fermi sphere. And in an excited state, you still have n wave vectors, but they will be other energy levels.
Why not all the ij equal to the same value since we have positives?
Because it will, no, this is completely forbidden, because then it means you will have 2k values that are the same, and this ansatz will, so this will, well, at infinite interaction, you see immediately that the wave function will vanish, because it will be anti-symmetrizer will be 0. And in general, it's, I would say, an hypothesis.
But anyway, no, you have a minus in the fate, and you have exactly a minus in the fate, but then
It vanishes.
it vanishes anyway.
Yes.
So how is it that in those derivatives you just have all the terms with the classes like Q, AQ, or PAP, and then on the line below you have Q minus P times AP minus AQ. Like how does it work? Where do you get the minuses?
Oh, from there to there, I use the cusp condition, so I have minus of the d over, yes. Because x is the relative coordinate, so d over dx is related to d over the x1 and d over the x2.
Okay, sure. Okay, thank you.
Sure.
That was my question.
Yeah, no, but thanks, because indeed the time is short, so I skipped some steps.
How do we create an excited state then with this?
Great. Thanks for the question. For the ground state, you have a set of, integers that or a set of ij like that. If I want to create an excited state, means that I take, for example, in place of occupying this, I occupy another one. So, in fact, this is a typical particle Hall process, and this type of excitations were studied in a second paper by Lieb, and I cannot resist. It's called the Lib1 and Lib2 branches, and it happens when you have. Okay, so just in a very, very few. So you imagine you have these energy levels occupied, and now you want to create an excitation. You can take an excitation at a given wave vector. You can take, for example, one dip in the Fermi sphere and bring it just above, or you can take the last occupied and bring it much higher. And these are two extreme cases that create the Lib1 and the Lib2 branches of excitations. And if you plot it in the energy versus k, so omega versus k, you have two branches, one like that and one like that are called Lib1 and Lib2. And all here is a continuum of possible excitations. It's just this boundary and this boundary that corresponds to these two processes. And all that can be derived by looking at all the possible ways you can create excitation on top of a given Fermi sphere or pseudo Fermi sphere. We have to stop, I guess.
Okay, let's